Hello, welcome to the walkthrough of the Elastic Bending Analysis module in Structures Office 1.0. There's some underlying assumptions that probably won't be any surprise to you. Plane sections remain plane. There's no warping of the section. St. Venant's principle, which is that a set of axial forces which sum to zero will have no axial force a short distance down that point of application. That the beam is initially straight, that the curvature is small, there's no shear effects included, and the section geometry does not change. For instance, it doesn't account for ovalization of a circular cylinder. The features, it works on any section that you build. In Structures Office, it handles multiple materials, beams constructed of, say, steel and wood. It does unrestrained bending, which is axial force and moments about the x and y axes. It does restrained bending, where the neutral axis angle is fixed. That might be useful if you are analyzing a stringer on a wing, where the wing dictates how that stringer is going to bend. It does a yield and ultimate stress check, and it does bending shear analysis, your basic VQ over IB, and is fully programmable. Before you can do an elastic bending analysis, you'll need to define what materials you're going to be using. So if we go over to Structures Office, I'm in the Materials tab here. You'll need to either connect to an existing database or create a new one. Let's say I choose Connect to an existing database and select the database I want to use. You get this warning that says, to update the material properties of existing objects, save the document and reload it. By existing objects, we mean things that are currently in memory. If you change the database out from underneath, what's in memory doesn't know about that until you save that document and reload it. So I go over here to Edit Materials, and let's say I want to create a new material. I click Add. You'll need to pick a unit system for that material. And let's say I want to do International Standard. The minimum values for elastic bending is the name, Young's modulus, Poisson's ratio. If you want to get warnings when a yield or ultimate is exceeded, you'll need to put in the values here for compression and tension yield in the longitudinal grain direction. The same thing down here for ultimate. And you want to set a material property, or the material color. You can ignore the rest of this. We don't use transverse direction and grain direction in 1.0, and this is for plastic bending, and we'll talk about that when we get to the plastic bending module. So another thing you need to be aware of is that the unit system of the material that you're using has to match the unit system of the document that you created. So if I look over here, I can see my SI. For this section document, I'm using the SI units. I could not use these materials. If I wanted to use them, it's not a big deal. You'd say click on that and create similar, and let's call it aluminum. SI, and click OK, and then I want to change this unit system, so I click Edit. Okay, and here's another warning. This says that the database is the sole authority. Adding a material will affect all the documents that we're using that material. So the next time you read that document, whatever the new values are will be the values read in. There's something you need to be aware of. And then to change the units, I can just click on this switch here to go back and forth. And also notice down here there's a lock material. If you created a material and you don't want anyone to ever change that so that it's just fixed, click Lock the Material, and no one can edit that material after that. In order to do elastic bending, there's some preparation that you'll need to do. For any section, you'll need to do 3 steps. One, define the geometry. The second step is to apply the materials for the elastic bending, and it'll have to have all the values that we just discussed. And third, it needs to be meshed, and it's meshed for 3 reasons that might seem a little surprising, but it does a back check after it's done its elastic bending analysis. It goes through and it sums up the forces on the section to see that the moments that it gets from the summation are the same as the moments that you applied. It gives a very accurate plotting of stresses on a section, and also it's used for calculating first moments for VQ over IT, bending shear analyses. So yeah, if you hold your cursor over anything, it will tell you what the ID of that object is and what material is being used. After we've done the preparation work, now we're ready to do a bending analysis, and let's start out with a unrestrained bending. I'll go back to that beam with a wooden beam with 2 metal straps on it. Let's go to computations and click unrestrained bending. Up comes this dialog box. You notice the units are in newtons and centimeters because our document is in international standard units. We need to give a name, axial force. Let's just give a moment about the x-axis for now. This is in newton centimeters. Leave that at 0. Grain direction is always going to be longitudinal in 1.0, and the beam is straight, so there's no radius value here. And then you just click apply. It'll tell me that I've exceeded the stress in the steel, and that's because we inputted values for the ultimate of the steel, and apparently we've got stresses above that ultimate. Then does a check by summing up the forces from the elements and seeing that it matches the inputs. So we're plotting right now strain, because underneath the stress strain plot you'll see this pull down and it says strain. If you change that to stress, it'll change the plot to stresses. And you notice this is steel, so it's going to be much greater than the stresses in the wood. And then it finds the greatest tensile and greatest compressive forces, and it adds points on the section. And point 0 is down here, and point 1 is up here. And it gives you the locations. It gives you the stress in kilopascals, the strain multiplied by 1,000, so you'd have to divide that by 1,000 to get the actual strain value. Then for the material of these points, it gives the yield allowables and the ultimate allowables, and you'll see that we've got a tensile allowable of 150, and we're greater than that, and that's why that error, that warning was thrown. It shows you materials that those points lie within, and then a multiplying factor for Young's modulus of the steel versus the wood. So it's 16.7 times, the Young's modulus is 16.7 times that of the wood. Now if you pick anywhere on the section, say we want to know what's the greatest value on the wood, we can get that by just clicking on the section, and it adds it. ID of 2, what the location is. You know, it's color coded. Stresses are green here, strains are red. We didn't give values for yields. We did give ultimate values for the wood, but no yield. And the material name. And everything is always, the multiplying factor always it takes the minimum E when it computes these relative factors. And you can, if you click on a section, you can delete it. Point, you can delete it. And down below here we have a point on the neutral axis and the angle of that neutral axis. So we know that this is 4.6310 is this location relative to the coordinate system. Total axial force, these values here are summations from the mesh. And they should be close to what we input, but they're not going to be exact because we're taking average values on the elements. As you increase the density of the the mesh, you should see things get closer to the exact inputs. What the minimum stress is and the maximum. Maximum's over here. Min and max strains and the resultant moment. And you notice that once we added a load condition to our section document, it'll show up here. If you double click on it, it'll open up again and you can reapply it. Another function you might find useful is plotting stresses down through the section along a line. So let's open up that load case we just created. And let's add points at the top and bottom of the section. Add a point at the top. Adding one would add a point midway. And I'll do the same down here. And then we'll need to give the 2 points that define the line. Look at the point at the top and the point at the bottom. And then I'm going to have to apply the stresses and then show a line plot. And if we change this to stresses, we'll see the stresses plotted along that line. So once the stresses have been computed over the section, we can now do some bending shear calculations. So let's go back over to the section and let's bring back up our load case and let's reapply it so that we have stresses on the section. And you'll notice that now down here the bending shear button activates, and if you click on that, you'll see we have an elastic bending shear. Now this is all relative to the locations of this neutral axis. So that's why it's a subset of this dialog. The width of the shear area, say we want to find the shear stresses across the bottom of this plate. That would be the horizontal distance here. That's 5 centimeters, and let's say we're applying 1,000 pounds. Now down below here there are two different ways to get your Q's and your stresses. One is by a box and another is by the particular shape that you built it with, like a rectangle. So if we do this by picking this point, we define a box, pick those 2 corner points, and then compute Q. You'll see we get our Q and our shear stress. Another way to do that is to click on the shape itself. We had a rectangle here that we want to get the values for. It was called steel top, and you'll see these two methods match. And this is done for, there's two different ways of getting this calculation for a number of reasons. One is it's checking to make sure that the methods are working without error, because they're totally independent methods that come up with these numbers. Another is that sometimes, say this wasn't a rectangle, say it was a channel, you couldn't get a box area to work. You could only do it from by picking the shape, or you only wanted a sub area of a shape, then you'd want to use the box force. So it's a check, and it also handles different situations. Okay, once you've got these values, you come down here to figuring out what the load on a weld or fastener is. So you've got to pick a source, and it could be this group or this group, and the box area is the top, and the shape area is these values down here. So let's say box force. It makes no difference because they're the same in this situation. And let's say the width is again across the bottom here, and the longitudinal spacing is 10 inches. That's if we had one fastener going down through there, then the applied load is this many newtons. I want to take just a minute here to explain a little bit more about this box area. Suppose instead the box area only went from this point over to this corner. Okay, now if I zoom in there, let's get out of the way here. Okay, you'll see that this calculation, if you multiplied it by 2, you'd get this number here. And the reason it's accurate is even though these triangles don't lie on a border, these do, they all lie inside, but these are partially, they straddle the border of the box. It does do a split, and it, of those triangles, and calculates how much area is inside. So it is accurate as long as the border of the box divides a triangle along one plane. If, however, you move this box up to, say, 11.01, now you get this error message. It says an element at the corner of the box lies partially outside of the box, which causes inaccuracy, and it says to increase the mesh. That's because this triangle right here is being split on this side and being split down below, and that the algorithm doesn't handle that. So it's just saying to get a more accurate number, create a denser mesh, and the error produced by this will be reduced. So another, if you wanted to do a hand check, recall that you compute Q by taking the area that's enclosed in whatever it is you want to sum up on, times the distance from the CG of that area to the neutral axis, which you know from here is this number right here. And then you've got to, if you're doing multiple materials, you want to use this number here to multiply that area. Now, if you so you wouldn't want to calculate on an area that crosses material boundaries. That wouldn't work. So just keep aware of that, and I guess that covers bending shear stresses. Thanks for listening. So the last thing I want to cover in this elastic bending module is the restrained bending. Let's go back over to this section, and let's click on, in the computations, restrained bending. And up comes this dialog box, and it is virtually identical to the unrestrained bending, with the exception that we now input the neutral axis angle and the moment about the neutral axis. So instead of moments about the x and y axis, we're now talking about a moment about a neutral axis. So we can say, got to give it a name, got to give it a unique name, and the angle, let's say that's 45, and let's make that 100,000 and apply. And you'll see now we have stresses plotted on that section based on this neutral axis. And you'll see the moment about the neutral axis is here, and it's fairly close to this, and we can do, say, a line plot down through there. Just run it across and show line plot and see stresses. So bending shear is identical. The only it's really no difference there. Of course, here when we're applying a load that isn't oriented vertically, it's the VQ over IT doesn't apply in this particular load case. So that wraps it up. Thanks for listening.